Alright, in this review video we're going to talk about enzymes. So what are some of the things we know about enzymes? Well, for one, they catalyze a reaction. In other words, what that means is they speed up the reaction at physiological conditions. And so by physiological conditions, I mean that we're talking about conditions that the cells can live in. So normal temperature, 37 degrees Celsius, which is 98.6 Fahrenheit body temperature, normal pressure, normal amounts of reagents and products and so forth. Right? In chemistry, we can speed up a reaction by heating it, give it more energy. Well, we can't do that with cells, so we need enzymes to catalyze the reaction. We know that it binds the substrate at an active site. And this active site is very, very specific to that substrate. So an enzyme is very specific to one reaction usually. And this also is why the fold of the protein, the fold of the enzyme, is so critical, because if you change the fold, you will change that active site and it's no longer going to be able to catalyze the reaction by binding to its substrate and speeding up that reaction. This is one of the ways that noncompetitive inhibition also works. An allosteric site will be bound by an inhibitor, and that changes the fold of the protein, prevents it from doing its work. So we're going to talk about that as well in this video. All right, we'll talk about how it catalyzes the reaction and the binding of the substrate at the active site, as well as inhibition and so forth. One other thing we know about enzymes is that they are not used up by the reaction, right? So because this is a catalyst, they are not the enzyme is not actually part of the reactants and then part of the products. They're just used to speed up that reaction. So it's not used up in the reaction. And this is one reason that the enzyme can catalyze a reaction, then go bind the next substrate and catalyze that reaction. So the same enzyme can catalyze a bunch of different reactions. Now, the reaction is always the same reaction, it's just doing it a bunch of times because the enzyme's not used up in the reaction. All right, so let's talk a little bit more detail about the reaction that's occurring as an enzyme catalyzes it. So one of the things we talked about was glucose. We know that glucose, when it's oxidized, will give off energy. So this reaction releases energy. However, we also know that you can leave glucose out at room temperature and it's not going to explode, even though there's a lot of energy in it. We talked about this in class with sucrose or table sugar, right? I can be tossing around a packet of table sugar and I'm not worried about that exploding in my hand, even though there actually is a lot of energy, chemical energy in that sugar. The reason is there's a large kinetic barrier, right? That's why sugar can be left out in room temperature without a loss. So when we look at the reaction, here is our energy of the reactants, right? So the energy of the reactants is right here. The energy of the products, that final state, is right down here. And so we know that this is a downhill reaction. Energy is being given off, which means that my delta G, the difference in energy from beginning to end, is going to be negative. This is an exergonic reaction. It is a reaction that gives off energy. One key thing to note, enzymes do not change thermodynamics. In other words, if this reaction had a positive delta G, if it was an uphill reaction, all right, so what would that look like? Look down in the corner here. So if this was an uphill reaction, it might look like this. Well, that would be a positive delta G. Well, an enzyme can't make an endergonic reaction occur. Enzymes do not change the thermodynamics, do not change delta G. All right? So don't forget that. But what we have here is we have a transition site or state. This is an intermediate that the reactants have to go through to get to the products, and this can be high energy. This is why sugar just doesn't naturally explode in your hand, because it has this high energy of activation. So this energy of activation is right here. That energy of activation is the reason that even though this is a favorable reaction, a spontaneous reaction, because it's exergonic, it's not going to happen automatically. Right? And so what an enzyme does is it lowers the energy of activation. So if I look at the catalyzed version of this reaction, shown here in green, the catalyzed version has to start at the same spot and it has to end at the same spot. It cannot change the delta G. But what it does is it lowers that energy of activation to make this reaction able to happen more frequently. All right, so the new energy of activation would be much smaller. However, the delta G doesn't change, the energy of the reactants, the energy of products doesn't change. All that an enzyme does is lowers the energy of activation. Well, how does it do this? We talked about 3 different mechanisms in class. One is the nuts and bolts analogy. So even though a nut and a bolt fit together perfectly, there's a lot of random kind of energy required to get them together. I can't just throw a bunch of nuts and bolts together in a bag, shake it up, and expect all the nuts to wind onto the bolt. I have to physically put them there. So the enzyme basically is physically bringing 2 substrates together. And in this case, it would have active site for both of those reactants, and then when they bind, it helps bring them together, and that's going to create a reaction or catalyze the reaction where A plus B becomes AB. All right? It can also stabilize a transition state. So if the transition state, if that energy that was up here was unfavorable because it had a certain charge, hydrophobicity, or something like that, if you stabilize it, that's what's going to lower that energy of activation because you've stabilized the transition state. You've brought the transition state's energy down, and then that lowers the energy of activation. And if it's an enzyme that's breaking, if it's undergoing catabolism, so it's breaking bonds, one of the things it can do is help stress that bond to make the break a little bit faster. So that's what we're kind of showing down here. The enzyme is stressing that bond. All right, so if you were asked to draw some of these things, so what would a non-spontaneous and endergonic reaction look like? Well, the endergonic reaction is when your reactants have a lower energy than the products. And so there still might be an energy of activation, but the delta G for an endergonic reaction, the delta G is positive. All right. Now in B, if we're talking about a spontaneous reaction, all right, spontaneous reaction where the delta G is negative, that occurs instantaneously. In other words, without the addition or without an energy of activation, that spontaneous and automatic one would be like this. All right, this is our delta G. There is no barrier, there is no unstable transition state. That thing is pretty much going to happen automatically. Now, most reactions are kinetically stable, at least to some extent. All right, so spontaneous means the delta G is still negative, but now we have that energy of activation. And different reactions can have different energy of activation. So if some things are very explosive, for example, TNT or whatever, your energy of activation might be quite low, but there still usually is some energy of activation. So C, the spontaneous reaction, again, our delta G is negative. That's why it's spontaneous, but it's kinetically stable because we have that energy of activation. And so then if we look at the catalyzed version of this, again, we know that the catalyzed version starts the same place, it just lowers the energy of activation, and it ends the same place. That's our catalyzed reaction. All right, so last, let's talk about inhibitors. So we know that the substrate, all right, so this would probably be the reactants, binds at the active site, all right, so the active site is perfectly fit for it, has perfect interactions, positive attracted to negative, hydrophobic interactions together, all those interactions we know about. That's the active site. So a competitive inhibitor, competitive inhibition, is when the inhibitor binds in the active site. So it basically outcompetes the substrate. It blocks the substrate from being able to bind because the competitive inhibitor is in the active site. So the inhibitor binds in the active site. Then we have a non-competitive inhibitor. This is where the inhibitor binds to an allosteric site. This is a site on the enzyme protein that's different from the active site. But what happens is when this binds, the active site changes because the protein changed structure. And so that's the non-competitive inhibitor, because now it still inhibits this substrate from being able to bind the enzyme, therefore inhibits the enzyme from functioning. This non-competitive inhibition is one of the ways that metabolic pathways are often regulated. So we have this long series of reactions here where A is the original starting point and D is the final product that the cell needs. Well, if the cell has none of D, it needs more D, then it needs this reaction to be going. But if it has a lot of buildup of D, then it has enough. And so the final product will often be used to come back and block the activity of enzyme 1. This way, when we have enough of D, enzyme 1 is blocked. We want to block it early in this process. And so we stop these reactions. And then when we start to run out of enzyme D, when it's no longer there, we no longer have that inhibition, and the reactions continue forward so that we can make more D. And then when we have a lot of that again, it can act as the inhibitor. But because D looks very different from A by this point, right? The enzyme 1 active site is perfectly set up to bind to A, not to D. D has to bind to the allosteric site, and therefore is a non-competitive inhibitor. And that regulates this reaction so that we have the reaction going when we need more D, and we have it stopped when we don't have enough D. So always remember, the final product tends to be the inhibitor, and it has to inhibit one of the earliest enzymes in the reaction. All right, there we have it about enzymes.